In this lesson, we're solving separable differential equations that have the form y dash is equal to just a function of y. Now you'll notice there's no function of x in there, or the function of x you could say is 1. So they're still able to be separated because they're in that form y dash is equal to the function of x times a function of y. So we can just use the usual methods, and there's nothing really new to learn here except just to practice with things looking a little bit different. We use the usual methods. The right hand side will become 1 because if we're dividing both sides by our function of y, then what's left over there is just 1, and that naturally integrates to something really simple, just x plus a constant. We have got an optional extra method. Now this is very much optional. If you don't choose to use this, you'll be completely fine, but maybe it's a handy thing to know in case you're feeling stuck or you've got something that's difficult to integrate. It could be a good workaround. You can take the reciprocal of both sides and then integrate both sides with respect to y. So with this simple example here, I'll do it our usual way, and then I'll choose the optional method, and you can see if you like the look of it. So our usual method is to rewrite y dash as dy dx, divide by our function of y, so that gives me 1 over e to the y on this side, and that will leave me with 1 on the other side. Now I can integrate both sides with respect to x, performing the same operation on both sides. The dx's cancel as usual. Now integrating here, I've got e to the negative y, don't I? So that integrates to e to the negative y with a negative out the front. Now when you're integrating, don't forget, always differentiate what you get to check it takes you back. The negative will come down the front, it'll vanish, and we'll get this. So that seems good. And on this side, the integral will just be really simple. 1 integrates to x, and we add our constant. So now I need to get e to the minus y by itself. So I can multiply both sides by negative 1. So I get negative x. I could write minus c. I could even write plus c, acknowledging that c's changed. But if c's changed, I tend to like to call it d. That's just me. And now I can write this as a log and say e to the power of minus y is equal to negative x plus d. And now we're nearly there. We've got minus y. So to get y, we just need to multiply both sides by negative 1 again. And we can write log with a base e, or ln, of negative x plus d. Now, it doesn't make too much difference what letter you have there in your general solution. It could have still been a c, and you're still going to solve it exactly the same way when you find particular solutions. Now, using this optional method, taking the reciprocal of both sides means that our question, which notionally looks like this, can be rearranged just taking the reciprocal of both sides to get this. Okay. Now it says to integrate both sides with respect to y, and this will make sense if you consider that integrating this side with respect to y, we can pay respect to y because there's y's on it, but on this side, if we integrate with respect to y, squeezing it in there, I didn't leave quite enough room, the y's will actually cancel. So what we get here is the exact same thing. See how we've created the same thing. Now, is that really much of a hack? Well, it might be handy on certain types of questions and for other different sorts of functions. For this one, we've really just got to the exact same place. These are just on two different sides now. So rather than dividing by the function of y, we can do this reciprocal. I would recommend not doing it this way. I would cement the process that you already know, and maybe just keep this one in the back of your mind for other things. Potentially in extension 2, it might be handy. In extension 1, probably just sticking to this stuff is the go. Now in this lesson, we're looking at separable differential equations where the function of x is equal to 1, which means they're of the form y dash is just equal to some function of y. So the most famous type of equation like that is exponential growth and decay. Now we've already studied these in year 11. So we've seen that they've got this basic form, y equals something outside of e to the power of something. And we can see that when we differentiate those, this should be revision. We're just bringing the k out the front, and we end up with k multiplied by the entire original equation itself, which means we get k multiplied by y. Now what this really means is that the first derivative is a function of the population itself. Now mostly we replace x with t because we're generally looking at time when we're thinking about how things grow or decay. When k is greater than 0, we've got growth. When k is less than 0, we've got decay. This should all be revision. Now it's important to note here though that y dash is independent of time, and now perhaps that we've learned this a while ago, this can really sit in our minds and make some sense. If y dash is independent of time, then it doesn't matter where on the graph along the x-axis or the t-axis we look, what we find is that the rate of growth is very much just related to the amount of the quantity that we have. So if it was a population of, say, rabbits on an island, then the rate of change of that population of rabbits is going to depend how many rabbits you've got. You've got to have rabbits if they're going to have baby rabbits. And if you've got some radioactive isotope that's decaying, perhaps it has a given half-life that you know, then the rate of change of how much you have depends completely on how much you have, not the time that you're looking at it. So rather than just blindly going ahead and saying it's a separable differential equation, I'll just solve it, it's y dash equal to a function of y. Where's the function of x? I want you to think about why there is no function of x. It's because these are a type of equation that by their very nature don't depend on what's happening on the x-axis. So now let's look at an example. We need to solve y dash is equal to negative 3y, and then we've got a particular solution to find. So the general solution, then the particular one. So this should be quite straightforward for you by now. We need to change y dash into dy dx. We need to divide by the function of y. So we can have negative 1 over 3y, or 1 over negative 3y, and that leaves us just with 1 on the other side. Then when we integrate with respect to x on both sides, on this side, we're going to have negative 1/3 ln y, with our absolute value brackets there. Our dx's obviously have cancelled. And over here we have x plus c. So tidying up, we need to multiply both sides by negative 3. That will give us ln y here, and we'll have negative 3x. We could still call this c, but now we're in the habit of calling this d. And now we can say that e to the power of negative 3x plus d is equal to the absolute value of y. Now, we can do two things at once here if we're getting good at this. We need to drop our absolute value brackets around the y, but we also need to generate a constant here that stands for e to the power of d. Actually, we'll do it in 2 steps so that we're not confusing anyone along the way. So we can say that a e to the minus 3x equals the absolute value of y, where a is greater than 0. And now if we change it to just y instead of the absolute value of y, then we can change our constant from a to b, acknowledging that b is any real number. And we can use a variety of ways of writing that out, or you can literally just write it. So that's our basic general solution. Now we need to say when x equals 2, y equals 50. And find our particular solution. So subbing that in, we have 50 is equal to b, e to the minus 6, which means that b is equal to 50 over e to the negative 6, or 50 e to the 6. So now when we go to write out our solution, we could just put our 50 e to the 6 in like this, but we can see already, and when you've done a few of these, you'll get good at it, we can see that these indices are going to talk to each other. We're multiplying the bases are the same, so we need to add the indices. So we can cut to, I'll do it on the next line, we'll leave that there. We can put 50e to the minus 3x plus 6, or 6 minus 3x, whichever you prefer. And that is our solution to this problem. Now, while we're looking at exponential growth and decay, let's remind ourselves about the modified version. We saw these formulas already in year 11. They might have had different letters in them. Again, we usually use t in place of x, but here we're just looking at the shape of the equation, the fact that we've got constants out the front here, here, and here, and that when we differentiate this basic form, we just get the k coming down at the front of this term. And yet if you look at the b e to the kx, it's clearly equal to y minus a, which is why we can write the first derivative like this. So when we see a first derivative that's in that kind of form, and we go to solve it now using our separation technique, sure, we've already learnt the skills to solve this, but what I want you to do is combine your understanding of how to do this with the concept that we already learnt in year 11, so that you're really thinking about what this means. And remember, what it means is that the amount of growth that you get in one of these situations is not proportional to the population itself, it's proportional to the population plus or minus some constant. So examples that we saw in the past were perhaps something drying out, but it can only ever get back to a certain humidity that it had in the first place, or perhaps something that's cooling down and it's going to slow down because as it cools it will finally reach room temperature, or a situation like that. So when we go to solve this, we've actually got 2 choices. We could say, hey, this is a function of x multiplied by a function of y. This doesn't look like a function of x, but it could be 2x to the 0. Now all that means is that we could leave it there when we divide both sides by a function of y. We could leave the 2 and bring that over, or we could say this whole thing is a function of y, and we could bring the whole lot to the left. It doesn't matter too much. Now if I choose to bring the 2 along for the ride, then what I end up with is 1 over, let's expand this out, 2y minus 200 over here, and I'll have a 1 on this side. So when I integrate both sides with respect to x, I'm going to say, well, this isn't quite a perfect question. Let's change this to a 2. Let's change this to a half. And now on this side, I've got half ln 2y minus 200 is equal to x plus c. And tidying this up, I need to multiply both sides by 2, which gives me a 2x over here, and the constant has now changed. Let's call it d. So e to the power of 2x plus d is equal to the absolute value of 2y minus 200. So I've got a e to the 2x is equal to 2y minus 200, still in the absolute value brackets because we're acknowledging that a is greater than 0. So now when we drop those brackets and say 2y minus 200, we can change the constant and acknowledge that b is any real number. And then we'll need to add 200 to both sides. And then divide both sides by 2. Now when we do that, b divided by 2, well, b is just a constant, so we could just now call it a different letter. Let's call it c again, I suppose, or we used c. Yes, perhaps we should call it e. No, e is not appropriate. Let's call it f. Now, it wouldn't be wrong to actually just stick with b, but we're acknowledging that it's changed. Now, all we've got there is a constant. If we'd done it the other way, I think it would have been more straightforward. So as you get a feel for this, you can decide, hang on, I might just leave the 2 there. Why don't we just actually bring on this side the 1 over y minus 100, because that way when we integrate this side and we've got a 2 on the other side, our working is going to be much more straightforward because this is ln y minus 100 here. And we've got 2x already plus 6, so we're actually a step ahead. Now you can follow through and see that the working there is going to be much the same, but at the end here we'll get straight to having 100 plus our constant, and we won't have to divide everything by 2 because we've considered that way back at the start. So embrace flexibility and just think about what will be easiest to integrate as you go. But don't be afraid to just make a choice. Don't spend too long trying to decide what's the easy way, because the way that you can see to do is the way to go. If you get stuck, that's where you might want to backtrack and say, well, perhaps I should have made a different choice at the start to find something I actually can integrate easily.